All right, welcome to this explainer of Stanford's incredibly famous CS231N lecture. Today, we're going to completely unpack the core engine of artificial intelligence. We're stepping virtually into a Stanford computer science lecture hall to decode the, frankly, seemingly magical processes of backpropagation and neural networks. If you've ever found yourself wondering how exactly a computer actually learns from data, well, you are in the exact right place. So let's dive right into this. But first, just to truly ground us in that authentic Stanford classroom experience, let's quickly rattle through some crucial housekeeping. Yes, assignment 1 is officially due Thursday, April 20th, right at 11:59 p.m. on Canvas. If you hit a wall, TA specialties are already posted up on Piazza. Oh, and definitely keep an eye on your inbox. You're going to be getting an email later this week with details on how to redeem your $100 in Google Cloud credits. Okay, now that we've got the standard undergrad syllabus logistics out of the way, let's transition into the heavy mathematical concepts that are quite literally shaping our future. Section 1, the optimization landscape. Okay, to really understand machine learning, we have to start with our core goal, finding the absolute perfect set of weights, these are the internal parameters of the network, to minimize our error. And in ML, we call that error loss. Higher loss means your AI is doing a terrible job. Lower loss, it's getting much smarter. So, imagine the entire spectrum of every possible weight combination in our neural network as this vast, sweeping, mountainous landscape. The altitude of the mountains actually represents that loss. Our mission is to trek all the way down to the absolute lowest point in the valley. But here's the catch, and it's a big one. We are navigating this rugged landscape completely blindfolded. Training a neural network is exactly like a blindfolded person, trying to feel their way down a mountain using only their feet. They feel the slope of the ground, determine which way points downhill, and then they take a single step. And here is what that literal step downhill actually looks like when we write it in code. This is the vanilla gradient descent algorithm. It's basically an endless loop where the algorithm evaluates the gradient. Now, the gradient is just the mathematical representation of the slope of the ground right beneath its feet. Once it knows that slope, it performs a parameter update. That simply means it changes its weights to take a step in the exact opposite direction of the slope. So it feels the incline going up, and it intentionally steps down. Section 2. Calculating the gradient. So, the big question here is how on earth do we mathematically feel the ground to make sure we're actually moving toward the bottom of the valley and not accidentally hiking further up the mountain? Well, we have two main ways to figure out that slope. First up is the numerical gradient. Think of this like taking a tiny, tentative step in every single possible direction, measuring how the altitude changes, and then kind of guesstimating the slope. It's super easy to write the code for this, sure, but it is incredibly slow, and it only gives us a rough approximation. On the flip side, we have the analytic gradient. This uses pure calculus to find the exact, mathematically perfect slope. It's lightning fast and entirely exact. But because the math gets ridiculously complex, it's incredibly error-prone for programmers to actually code by hand. Which brings us to a massively important rule of thumb for AI researchers. In practice, you absolutely must derive the analytic gradient so your network trains fast and perfectly. But, and this is a big but, to make sure you didn't drop a negative sign or make some calculus mistake that ends up sending your blindfolded hiker marching straight off a cliff, you always check your implementation against the simpler numerical gradient. It serves as the ultimate reality check for your math. Section 3. Mapping computational graphs. Now that we know we need to use exact calculus to find our way down this mountain, we run into a pretty huge problem. Modern AI models are intensely, mind-bogglingly complex. We can't just write out one giant calculus equation for them. It's impossible. We need a map. So instead of dealing with dense, impenetrable walls of calculus, like that intimidating formula for hinge loss right there, we do something brilliant. We break them down. We visualize these complex mathematical functions as graphical maps. Every single mathematical operation, whether it's a simple multiplication, an addition, or a full loss calculation, becomes an individual node or a bait on this graph. And the data just flows through these nodes, step by step. Let's actually look at a really simple example of this forward flow in action. Here, we're calculating a basic function, f equals x plus y times z. Notice how our inputs, x, y, and z, enter from the left side. X and y flow right into an addition gate. That gate outputs a value, which then flows smoothly into a multiplication gate along with z. And bam, that yields our final output. This left-to-right movement, we call that the forward pass. It's exactly how the neural network makes a prediction. Section 4, backpropagation. The engine. But here's the thing, just making a prediction isn't learning. Real learning only happens when we figure out our mistakes and correct them. And that introduces us to the true hero of this entire explainer, backpropagation. This is the incredible mechanism that sends the gradient signal backward through our map, starting from the final loss all the way back to the initial weights, telling every single part of the network exactly how it needs to change. What's absolutely fascinating to me is how this backward flow actually works. If you look closely at the individual mathematical nodes, you realize that aren't just dumb calculators. During backpropagation, each type of gate takes on a very specific, almost human-like personality when it handles that backward flow of gradients. Let's look at their specific jobs. First up, the max gate. Remember, in a forward pass, a max gate's only job is to simply output the highest of its inputs. Because of that, during backpropagation, it acts exactly like a network router. It takes the incoming gradient signal from the right and routes it perfectly, fully intact, straight down the specific branch that had the highest forward value. It completely and totally ignores the other branch. It's effectively routing the learning signal to the loudest input. Next is the add gate. Now, the add gate is a pure egalitarian distributor. Because addition inherently impacts the output equally, no matter what the input values are, when that gradient signal comes flowing backward, the add gate just takes it and distributes it equally to all of its connected input branches. No favorites, everyone gets the exact same learning signal. And finally, we have the multiply gate, which essentially acts as a switcher. Thanks to the basic rules of calculus derivatives, a multiply gate takes the gradient flowing backward and actually multiplies it by the forward value of the opposite input branch. It literally switches their influences. So if one input was super large, it makes the gradient for the other input huge, forcing it to learn a lot faster. When you put the whole shebang together, it looks exactly like this. During backprop, those red numbers, which are our gradients, flow strictly from right to left. Our nodes seamlessly work together as routers, distributors, and switchers, perfectly pushing that mathematical signal all the way back to the very start of the graph. It's just an elegant choreography that tells every single weight exactly how to step downhill to reduce our error. Section 5. Scaling to massive networks. So far, we've only been looking at tiny, toy examples with maybe 3 or 4 variables. But to build actual, real-world artificial intelligence, we need to prepare for a massive, massive shift in scale. I want you to try and imagine what happens to our descent down that mountain when our inputs suddenly transform. What if X, Y, and Z are no longer just cute little single numbers like 2 or 5? What if they are massive, 4096-dimensional vectors? Because that's exactly what happens when we start processing high-resolution images or huge blocks of text. The math suddenly explodes in complexity. Think about it. If you have a 4096-dimensional input vector flowing into an operation that then outputs another 4096-dimensional vector, calculating the exact derivatives requires building what's called a Jacobian matrix. And the dimensions of that matrix? It's 4096 by 4096. That is nearly 17 million elements for a single tiny operation step. It's almost absurd. That gasp-inducing size perfectly illustrates exactly why modern AI absolutely relies on heavily vectorized code running on specialized GPUs, and why we have to process data in small chunks called mini-batches, just to keep our computers from literally crashing. But when you do manage to scale this math up correctly, the results are completely world-changing. This right here is the iconic architecture of AlexNet, a truly breakthrough convolutional neural network. Every single box, every connection you see is an operation inside a massive computational graph. The simple, elegant rules of backpropagation, routing, distributing, and switching those gradients scale up perfectly across this giant structure to power revolutionary image recognition capabilities. And honestly, as models get even more complex, the graphs just become staggering. Just take a look at this dizzying graph of a neural Turing machine. The sheer scale is awe-inspiring. Yet despite the apparent chaos of all these connecting lines and nodes, the foundational concepts remain completely unchanged. The forward pass calculates the loss. The backward pass pushes the gradient through the gates. The weights take a step down the mountain. It's all the same. Which really leaves us with a truly profound question to ponder as we wrap up. We've seen the simple local mechanisms, right? An add gate distributing, a max gate routing. But how exactly do these microscopic, rigid mathematical gates combine at such an enormous scale to create machines that can ultimately learn, recognize, and maybe, one day, truly reason? How does the simple, metaphorical act of feeling a slope and walking down a mountain mathematically build the intelligence of tomorrow? That is the absolute magic of machine learning. Thanks so much for joining me on this explainer of the CS231N lecture, and remember to keep questioning the algorithms that shape our world.